Great. So we're back at another Hacking Hours. Um, uh, I have the usual house guest, Alexander Mazureux, who got a very good introduction last week. Thank you for joining, Alexander. And I'm also excited to welcome Kade Heckel, who's been developing a very exciting JAX-based spiking neural network library called Spyx. Is that correctly pronounced? Um, And Kate, I'm really happy to have you here because I mean, there are a lot of different spiking neural network libraries out there. We'll get back to that in a second. But I think JAX is a particularly interesting beast because it's very functional in its approach. So we can do very interesting TPU-based optimizations. And I know you've hacked a lot on this, so I'm looking forward to this. I wonder whether you can just briefly introduce yourself, tell me what you're working on before we get started.
Yeah, sure. So I just finished up a master's. I did a master's degree at the University of Sussex last year in spiking neural networks and neuroevolution. Then I just finished up a degree here in Cambridge, England, on a. I was doing another machine learning master's degree, but I'm from the States and I'm heading back to the States soon. Um, but yeah, I created Spikes, which is this library. Um, Let me just click to the README if I can read. Um,
Get all the fancy
well,
catch lines. Ah,
yeah,
nice.
sadly it's not like beautifully rendered, but yeah. So I built Spikes as I wanted to do or study neuroevolution for spiking neural network optimization, and I found that there wasn't a really I wasn't thrilled with like the neuroevolution options in PyTorch, but there was a really great library that had just come out called EvoSax inside the JAX ecosystem for doing evolutionary strategies for optimizing like anything, like neural networks or other like continuous valued problems. So I decided like, hey, it might be pretty useful to build a JAX-based SNN library. It'd be a good learning experience for one. And like the initial focus was like, yeah, let's get an SNN library that you can use end to end with this evolutionary strategies library, so you could have like really like you could optimize it. Like I was just focused on like end to end, like have it actually play nice
Mm.
because you couldn't use like JAX based. Um, like it'd be pretty clunky to optimize the parameters of the SNN in JAX and then pump it into like SNN Torch or like a PyTorch based framework. Um, and so I ended up creating Spikes just to like do this neuroevolution task, and then kind of got not carried away, but I had lots of fun with just like the ML systems of how do we actually just optimize and make the inference efficient. Period. Um, so the reasons why JAX is an interesting ML framework, or like why I always like advocate like, hey, you should try JAX, is because the functional paradigm allows for some really neat tracing capabilities. Um, so you can just in time compile or even ahead of time compile like entire workflows, and then you get pretty good speed ups and efficiencies when you're running it on GPU. Um, and that's everything from, you could just in time compile your WAS function so that it's dispatched to the GPU as like a combined operator.
Mm.
But you can even go much deeper than that in terms of entire training loops where you're loading data, feeding it into your neural network, calculating the loss, updating gradients with your optimizer. You can do all of that end to end in JAX in a just in time compiled fashion if you build the training loop right. And you can get pretty obscene speed ups, especially on like the data loading, which was like one of the big things I found was I was able to, like, I was training not like the networks that you've like of sizes you would see in like spiking Heidelberg digit benchmark, when they're
Mm. Yeah.
like, oh, like let's investigate this like new mechanism, and it's like here's like a 3 or 4 layer SNN with like widths of 512, and I was able to get the training speed for that down into like sub 1 minute for hundreds of passes over the data set.
That is
um
really really cool. And I guess
yeah.
exactly you also answered kind of why the need for spikes, right? Because they are by now quite a few SNN libraries out there, but it is really this cool paradigm thing. But it also seems to me this is quite similar to what Triton or the newer version of PyTorch is doing, right? And I guess the difference between those is that it's easier with JAX because you have these functional components, but kind of the huge state that follows the PyTorch graph, where you have to carry along like this autograd kind of graph, makes it easier to do in JAX. Would you agree with that? Is that your understanding?
Um, yeah, along that line. So like when I started, also like there's been work going into improving Torch compile over the last year or so, but it really is true that um, like JAX was built from the ground up on this functional paradigm to enable just-in-time compilation and tracing to,
Mm.
basically translate into XLA very efficiently. Whereas with Torch compile, I'm not a Torch expert, but my understanding is since you start off with this very object-oriented, design pattern and everything, you have like the translation's not as easy per se. So it's not, you don't get as much powerful optimization just happening naturally as part of the process, or it's like difficult to get the same
Yeah,
types of efficiencies.
yeah,
Um,
I see.
so, and then yeah, in terms of like other systems levels improvements too, like there's now like there's like different types of extensions for JAX that you can use to help write lower level kernels and then package things in pretty nicely in terms of like Triton. But the cool thing is that, well, the other thing too is that Torch doesn't have, like, JAX is designed to export models or run models on both GPUs and TPUs, which
Yes.
there hasn't been a ton of work looking at running on TPUs, but I've been doing some reading on like kind of their design philosophy, and I think there's probably some like really interesting aspects of like the TPU architecture that could help accelerate these
That is
dense
so cool.
SNN simulators.
And I mean, I'm really looking forward to looking into this because I think it'll be fun to see what this means in practice, right? So how do you do kernel fuse in practice? Um, I just have one question because you mentioned a different types of approaches to do that in JAX, right? So I've noticed, for instance, you mentioned Pallas as a new approach, and that seems to be from the JAX native. I mean, still an experimental library, but is that the approach you would prefer, or what else should we do?
Um, I think Palace is probably a good direction to go in.
Mm.
So I a lot of the inefficiencies I think in like SNN training right now, if you're doing dense based computation, um, and when I say dense, I mean you're not doing sparse map moles, like you're materializing zeros and stuff like that.
Mm.
Um, like I don't think there's a lot of efficiencies from just taking your neuron model or like your activation function and rewriting that in C and then lifting that in as like a like new operation for, yeah, like JAX. And like I have the notebook that I have here that I guess we'll kind of pick through, kind of like shows that um like you may not like the difference between just letting JAX do JAX tracing operations versus creating like a Pallas kernel to do the same thing versus like I don't think you're gonna get much better improvement if you keep going down the tech stack until because like the problem is if you want to like use like write your own C++ version of the same kernel and
Yeah.
try to lift that into JAX, like you can do that. It's just now if you want other people to use it, they have to like compile it in. Like it's a lot nastier to get. It's not as portable. Um, and the nice thing
Yeah.
about JAX is that you can get really high performance without a lot of the portability issues of like, oh yeah, you need to like compile it in your own environment and make sure the
Exactly.
library is okay.
I think that's such a strong argument, and I mean, you also mentioned to me in writing before that with these methods you can actually get quite close to almost hand-rolled CUDA code, right? So we mentioned spiking jelly, sorry, which is another library, kind of stitches together strings of CUDA kernels, compiles them, and then runs it. So it's very low level, right? But with these relatively high level methods, you can still get extremely good performance in JAX. So that's enticing, right? Because that means in principle we can spend a very little tiny bit of time developing, but then get quite a bit of performance out of it anyway. Um,
Yeah,
and
that's probably what I would say is a big selling point of JAX and Spyx is just, or any other like JAX-based SNN library, um, is that you can write Python code that's pretty straightforward or pretty similar to what you would write with Torch. Um, but then when it gets compiled, just in time compiled down, you end up getting pretty similar efficiencies to like spiking jelly or some type of like higher performance like C based
yeah,
solution. But yeah, I think in terms of like where you end up losing a lot of training time in SNNs or even like just training neural networks in general is more so from like data loading, and like shuffling and those other like operations outside of
yeah,
just the forward pass. So
yeah.
like
That
in
makes sense. Yeah,
yeah, and like the loops that I have written for Spyx and like in the documentation, um, like for example, I'm for a lot of the times, especially when you're looking at GPUs now that have like 80 gigabytes of VRAM, or we're getting into the hundreds now. Um, there's lots of spiking based data sets that you could efficiently compress into, like if you pack all the spikes into unsigned integers, you could fit those all into VRAM on, maybe that's not
mm,
the case if you're working with like petabytes of, or terabytes of streaming data for autonomous driving.
sure.
But that's like industrial scale engineering at that point. But for like research purposes, you can fit these data sets completely into VRAM, like into the HBM. Um, and then you can just unpack those batches of spikes as you're feeding it into the network. And then you can also shuffle those rows all within the high bandwidth memory of the GPU, and it's a whole lot faster than having to go out to the like CPU RAM, even if you pin the memory in CPU RAM.
That's
Um,
amazing. Yeah,
so like, and again, like thanks to JAX, you can just in time compile this whole operation so that way it sends off all of these kernels to the GPU to execute in a run ahead fashion. So it takes like the Python interpreter out of the critical path and the thing just burns really like it's pretty fast. Um,
that's
but
yeah, brilliant. Yeah, so
uh,
so so I think, I mean, I guess there are two things here. One thing is to then get things going. First of all, like just making sure you can lower this, but then second, there's this wrangling, like you said, thinking about you're shuffling your data and so on and so forth. And if you can then just clunk everything into the same device, you get tremendous speedups. So I'm really excited about this. I also just have to say that I think it's pretty insane, Kate, that you did this in your masters, right? I mean, you wrote like research level software, which is like seriously useful for the scientific community. So absolutely amazing efforts
yeah, I
there.
mean there was really great like SNN Torch is a really great library and like provides like it's PyTorch based from the name of course, but in terms of like making it like it's not making it very clear like here's probably what you need or what you should have for doing spiking neural networks. And then my like the and building the library was essentially just like, well, I need to translate this to JAX, which wasn't too crazy. It was more just learning the functional programming, like sharp edges. Um,
Hmm.
and then like the systems level optimization was just like, oh yeah, like it makes sense that I should pack these, bits, which is I don't think Torch yet has like an integer packing utility for some reason, but JAX into you can pack in and out of like unsigned integers, which is pretty cool,
That's
and helps
amazing.
with
Yeah.
dealing with like these sparse data streams. Um,
Cool. We'll
but
send our love to Jason for his work there.
yeah,
But I wonder, like, Kate, what are we gonna do today? I mean, you mentioned like this GPU optimization, so being able to take some of these dynamics, right? We're talking about spiking neurons probably in specific, which are unfortunately recurrent. So is that the problem you want to tackle here as well? Like, or what are you thinking?
um, Well, we could. Like the first thing I started exploring this morning or looking more closely at how to optimize like the kernel fusion, just of like, hey, is there an easy win in terms of fusing together the like surrogate gradient function? So like say like super spike, which is I don't know if me zooming in here will zoom in for you, but
Oh,
um
is this more clear? Maybe I should hide
yeah,
the.
yeah.
There we go.
So like super spike, for example, you have to compute you have some like scaling factor, but it's one over the quantity of one plus a scalar times the absolute value of x squared. Um, so there's like a number of primitive operations going on in here. Um, and the question is like, well, if you just looking at this in code, if you don't, the question is like, well, how optimized is this underneath the hood when it gets sent to the GPU? Because that's kind of when you sit at like the JAX level of abstraction, you don't know like you, you don't know how good XLA is actually doing. So like that's the like question is like, is XLA doing a good job, or is there
Mm.
like something we can do to help it? Um, so in this case, we have the gradient, like the super spike derivative or gradient function here, and we use JAX just-in-time compilation to like compile it. And then we can create like a basic array here of just values to feed in, just kind of like a placeholder. Helps if I import stuff. Um,
It's funny. My editor is following you, but I can't see your cursor. But yeah, so I guess now you're
uh,
just trying to run it. Should we maybe test it out? Like, can we do something like this? Or what's it called? This is module to benchmark it.
oh, time it. Yeah, like I time it down below.
Oh, okay, perfect. Yeah,
But like for now, we'll just look at the
the
like
output.
the code generation
Yeah,
aspects.
cool, awesome.
Um, so the first part of like JAX has multiple stages in its lowering process. Um, you can find like the whole thing at like in the documentation. It's under ahead of time lowering and compilation. But the first thing JAX does is it, and I'm just going to read from the docs here, is it stages out a specialized version of the function you define. Um, so that's what they refer to as JAX-bers or JAX expressions. And then from there, it gets lowered into stable HLO, which is the input language for XLA's compiler. And then that HLO program then gets compiled into like something for the GPU or TPU, depending on your target architecture. And then from there, that gets executed. So this
Okay,
lowering process right here, actually, I think we could even, before we lower it, should just be jax dot make jaxper of Brad super spike.
so is what you're saying that basically the first step will be the internal non-XLA representation, and then later you would then get a specific XLA representation. But um, is it then correct that the JAX.JIT would then take it to the internal representation, which is not yet XLA?
Correct. Yeah. So like this, like the first step one is essentially making a this jaxper, which I don't know if it's populated yet for you. Um,
Ah, maybe I have to run them myself. Okay.
no, I added an extra cell just now. Maybe I have to save it or something.
So
Um,
I, okay, this kind of doesn't work as well. I don't think I'm running this on your machine, because I
yeah, I
don't
don't
think I have
think
all
we're.
the JAX dependencies installed. Hmm. Okay. How
Yeah, I
do I
don't
deal
think
with that?
we're on the same.
Can we maybe run this in a Python script and just run it in the terminal? Because I think we can share that. It's not as clean.
Yeah. Um.
Or you can share your
Here, let me.
screen.
Yeah, I can. I'll just share my screen if that doesn't hurt too bad for the stream. Um.
I just have to reconfigure.
Yeah.
1 second. Wait, how does... Are you sharing your screen?
Should be.
Great.
Looks like in the view.
Ah, here, watch stream. Okay, so then let me do this, and let me just blow you up here in the stream. So basically what you're doing now, I guess, is to import JAX and all these libraries, right? And then with this JIT notation, you then get the internal representation, which is somewhat optimized, which you can run in when you do grad super spike of some arbitrary array.
Yeah, so like the JAX just-in-time function decorator, what that does is you apply that to a function that is you want to do your best to make sure that the function that you're just-in-time compiling has no side effects.
Yeah.
Because it will compile. It's just there may be unexpected behavior in terms of like something you think is changing is not going to change. So if you have some stateful computation in there that it will, yeah, it might stay frozen at some value, and then you're not going to get what you're expecting. So
Okay.
JAX works around these function transformations. Everything is essentially like, since it is so functionally oriented, you end up with like you write functions and then you transform those functions or data in order to do what you need to do. So in this case, we import JAX, Spyx, which is the SNN library, Haiku, which is the deep neural network library that Spyx builds on top of. So kind of in the same way that like you can use PyTorch NN primitives or layers inside of SNN Torch, you can use Haiku neural net like layers inside of Spyx. And then Opdax is a library that contains optimizers like Atom or SGD. Insert your favorite flavor.
Right.
So yeah, here we define the gradient of the super spike function, which this is also built into Spyx, but it's inside of like a nested, like a function factory type situation. But since we just want the actual gradient function, array here we call V. So if we run like grad super spike on V, we get out like what the surrogate gradient values should be. And if we turn it into a JAXPer, which is this first process as part of like all of this tracing machinery that's built into JAX, you end up seeing this type of single static assignment expression, which is how JAX is able to help make things easily optimizable.
Exactly. So that's
Yeah.
really cool, because then you really have an XLA expression. It even
Yeah.
shows
So
that
like
as well.
from this
Cool.
single static assignment, then you can start doing the next process, which is moving to like you generate this stable HLO, which is what gets fed into XLA for compilation. So if we lower it, which will take it from this JAXPer into HLO, which is the XLA stuff, you end up with this output here. So there's some metadata, but again, it looks very much like a single static assignment workflow of each of the operations, like absolute values and multiplies and all that. And then the next like final step before you send it to the metal is to compile it. So then like this is like doing things everything step by step. All of this happens behind the scenes on the fly, like just in time, like when you're normally using JAX. So like for example, like when I define grad super spikes or super spike and I just in time compile it and then I call it here, this is the just in time compiled version of the function. It does all of these steps behind the scenes like the first time, and then it caches the generated code. So next time it's going to
Right.
be much faster.
Whereas
Uh,
when you do it manually, then you're forcing all that steps basically. So you kind of
yeah, this is manually walking through the process, but what happens is when you like go to run code normally, is you'll have like some amount of like compilation warm up time, and then the rest of the computation will proceed at like the fully compiled speed.
But is there then a
It's just
point of doing the upfront compilation? Like if the same procedure happens if you just did it, like what's the value of lowering this manually?
um for like debugging purposes and visibility.
Right.
So and like so we'll see, here's like the HLO that gets fed into XLA. We compile it using XLA, and then this is the like resulting output of XLA here.
That's pretty cool.
Which you can see that there's like this entry point, and it just calls into this thing called it calls this fusion, like divide fusion kernel. So the automatically divide or generated name was fuse divide. You can see that all of these operations here seem to have been bundled together into one. Um, that's been bundled into what appears to be a single fused kernel, which is pretty cool because what that's saying is JAX was able to see all these like numerical operations on like the input out, input tensor, and it bundles them all into like a single dispatchable thing to send to the GPU. Um,
Perfect.
so there's also like cost analysis tools in JAX.
Nice.
So I have to run these cells.
It's surprisingly fast. I mean, Triton can be really slow.
Yeah, I don't have direct experience with Triton. Yeah, so like this
Okay.
cost analysis can give you estimates on like the number of flops and stuff and this is all based on like the sample input you provide. So if you were curious about doing this with like ML workload, you would provide like a sample batch, and then you could see like, okay, like per batch I'm using, roughly these many flops or
Mm.
stuff. But this is like again, it's a debugging type of interface, not like a production, like don't bet on it type deal. Um,
But it's
so
nice.
then the
Oh, and now
question,
we get to Palace. Yeah.
yeah, and then the question is like, well, is this, it says it's a fused operation. It looks pretty efficient. Can we do better? Or is this actually already really good? So Pallas, which is this kernel language that's experimental but built into JAX as a is like a common interface that allows you to write memory, like more hardware aware or hardware specific kernels that can then be lowered into either GPUs via Triton or into TPUs via Mosaic, which is Google's other like DSL for
Mm.
TPUs. Um, and so the big difference between JAX and Pallas and how you write it is that JAX, like everything's functional, so you're not supposed to like, it's not a, you don't really overwrite variables per se in JAX. Um, Alice, you actually do get references, to areas of memory. They give you references, and then you actually overwrite those arrays. So it is different in that you actually are overwriting state. So it's not like a functional aspect anymore because you're working at the level of the hardware.
Okay, so that means every single parameter, for instance, here in your add vectors kernel would be references, not specific, like, um, not objects.
Um, I guess that is a misnomer in how they name it. They do behave like objects. Like it's not like if you were to print out the reference, I don't think you would get like a pointer, though I don't think you really are supposed to print these out because it's executing on the GPU.
Yeah, but
Um,
it's a bit like
but
Python, right? I
they,
guess everything in
yeah,
Python is mostly just like an object reference
yeah,
kind of. But you can still do
yeah.
like ellipsis
These
lookup.
behave, yeah, these behave more like NumPy arrays than JAX arrays, which are supposed to be immutable. Um,
Okay.
like in JAX, you can't explicitly, you technically don't set very specific indexes of arrays in JAX. What you technically do is create a whole new array with the modified values.
Yeah.
But that's That's all because of the single static alignment or single static assignment paradigm, which they want to do just-in-time compilation like all the way through end to
That
end.
makes sense. Yeah.
But yeah, whereas in Pallas, like you have mutable objects that you overwrite because you're working at like the lower level of the hardware. Um, so in this case, like their sample code is like adding two vectors, so like x and y, and then you output them. Um,
But it's interesting that you kind of de-assign them. You kind of take, um, you know, the x ref and assign to x and the y ref and assign to. Is it looks a bit like when you have HDF5 files, like you kind of unpacking kind of the underlying reference into an actual object. Is that similar to what's
yeah,
happening?
that's pretty similar to what's happening here because what's going on is these references are point to the high bandwidth memory of the DPU or
Mm.
the accelerator. Um, Also, kind of with the TPU, it's pointing to like some more distant level of memory hierarchy. And then when you do this assignment in, like with these, triple dots, you're reading that into SRAM. So you're bringing that memory in closer to the processing unit for, manipulating it.
Yeah, you kind of force it to materialize somehow.
Yeah.
Yeah. Okay.
Um,
Yeah, this is clear. So now you're just adding. You're taking these two, you know, tensors, and then you're adding them together into a ref. Oh, O ref. Sorry, maybe we should make this bigger.
yeah. And then when you want to go use this kernel, then you end up passing it into this Pallas call function, along with a series of metadata describing like the output shape, along with grids, like a grid and
Mm.
block sizes, which are necessary for when you want to chunk up larger sequences of input. Because now you have to worry about um, like how wide are the streaming multiprocessors on a GPU, or if you're using TPUs, like there are different hardware concerns about
Yeah.
like you need the blocks, you need like the last dimension to be a multiple of like 128, and then like other power of two considerations. Um,
Yeah, so grids and blogs are kind of, if people are not familiar with those are kind of nomenclature related to the GPUs that are organized, whose threads are organized in a specific way, right? So obviously you want to play with that architecture instead of against it, which is why you mentioned this power of two, right? Because everything is connected to that. I mean, I'm itching to see some runtime stuff. I mean, now you kind of did
yeah,
this instead, but you said you'd get to it. And now you made a super spike version of it. Perfect. Yeah, so that's the same algorithm before, right? But now
yeah,
you have an input x, that's the same we saw as before. You also have the output reference, so you take the input reference, unpack it, and then you assign the output into the output, right?
yeah. So this is just an element-wise kernel with all these different operations.
Great.
I just rolled instead of k, which is like usually, tunable parameter that you can specify for the function you want. I just rolled the 25 in there, but you could template this kernel. You could have a function that returns this kernel as the output where it has the baked in like constant there. Um, and then what we have to do is we go and basically write our Pallas super spike function, which does the Pallas call. Um,
Okay, yeah, and this is then the block specification. So you're specifying two blocks.
yeah. Um, there might be a slight. I might have to change this to that. Um, I had a slight editor issue right before we started because like cursor closed on me without saving.
Oh
Um,
God. Thanks,
but
cursor.
yeah,
But I guess
this
this makes sense because it's power of two. But
yeah.
also, you wanted to do this. Is this then the so you're having 32 blocks at once? Is that correctly understood?
So in this case, there should be 16 blocks of size 32. Um,
Ah, yeah. Okay, so you have a grid of 16 blocks, and each block is then 32. Okay, that makes sense.
yeah, 32 elements. Um, I'm still learning Palace, so I haven't gotten to the point where I like the 16 and 32, like those aren't entirely arbitrary. Those are related to like the overall size of the input. Um,
Yeah, which we
so
have chosen. So that also means if you had a different input, let's say you have a huge tensor, right? You would probably want to change this, and it probably also depends on your hardware, right? Because
Yeah. You would want the block shape to line up well with like the size of your streaming
yeah,
multiprocessors on your GPU, for example. But yeah, like there's again with like templating and like functions that return functions, you would want to build some type of method so you can specify like you can generate the appropriate kernel to match like the input. Um, but if we run like if we come down here to like again if we want to inspect like what does the generated code look like, because the nice thing about Pallas is you can fold in JAX like JNP like JAX NumPy operations into
I
Pallas and
I noticed that
it'll work.
that's really amazing, and I guess that's because there's one single correspondence to that operation. I mean, it's already been lowered down to HLO, so that would know exactly what to do
Yeah.
with that call,
Uh,
right?
yeah. So then if we come down here and we want to see like what's the Pallas like the lowered kernel from Pallas look like. So this is
Super
the
cool.
HLO that gets lowered from this Pallas kernel, and you can see that since it's a custom operation, you just see that it's a like a Triton custom op that gets spit out.
Wait, a
So like you
Triton.
don't have as much visibility into it, but you can just see that it's now like a very singular like entity in terms of the HLO. And then if we
Ah, okay. So
compile,
Pallas is basically built on Triton.
yeah. So Pallas is the intermediary between JAX and either Triton if you're doing GPU based workflows or Mosaic if you're targeting TPUs.
Now I see. That
Um,
makes a lot of sense. Okay, but that's really cool. So you kind of made a Triton kernel essentially
yeah,
that you just
yeah.
call as a single function essentially.
Yeah, and then when you go to compile it, now you just have this single HLO module that is the Super Spike Pallas kernel um, that's targeted for like this input shape. So like now when you look at the compiled entry point here, it's just this single line of calling the Super Spike kernel rather than um, up here where you
Yeah.
have a call to this fused operation, but inside of this fused operation, you see all the other things. Um, so the question is like, are the internals of this fused operation as fast as the whatever gets generated by Triton
Yeah.
that isn't visible in this, as
Exactly.
text
Exactly.
interface? So you can run the timing on these two things.
Ooh, that's what I've been waiting for.
Yeah, sorry.
No, 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 no,
Um,
no. I mean, this is amazing, right? I think it's really helping me understand exactly how all these components fit together. But it is, I mean, that's pretty much exactly what you say. Right? The question is, are these compiled Triton kernels connected with with Pallas, right, more efficient? Ooh, that is very interesting.
yeah, so that's the thing is you look at this and you see that the like JAX just XOA the optimization process like it was able to fuse those kernels together anyways, and all you had to do is write normal Python and not even care about like block sizes, grids, or shapes. Um, XOA was able to fuse that together just fine. Um, and then even when you like go into Pallas for like just trying to optimize a surrogate gradient function, and we're messing around with like block specs and all that jazz and refs, you end up with the same performance. Um, so like
That's
that really does show
interesting.
the power of JAX, or like why it's so neat. Um,
Do you think it has anything to do with the simplicity of the function, right? I mean, there's nothing interesting happening here in terms of memory allocation or anything. You're literally just applying an operation or a few operations, right?
um, I mean, if you're saying in simplicity in terms of like JAX being able to optimize that part,
Yeah, I mean,
or
in terms of
are you,
compute graph, actually, it's just like a sequential. You just do, and then that's it, right? So maybe a different question would be like, what is needed before this becomes a good idea to use Pallas, for instance? Do you know?
yeah, so like that's a good question. You can see a lot of speed up within just running a or inferencing a spiking neural network you can get from if you then spiking jelly does this too. It's called they call it a layer by layer execution. Um, so you can again get much better speed if you take like each linear layer and do a batch apply across like all of your time steps at the same time,
Yeah.
because the linear layer isn't time dependent. And then if you just execute your entire like the neuron model that follows the linear layer, if you just execute that across all of the time steps, and then you run a batch apply on your next linear layer,
Yeah.
um, you get much better. That's faster than if you run the entire like SNN from input to output, or like input to logits for every time step in a row,
Yeah.
because of like memory accesses and everything like that. And then within the process of doing the stateful computation of just the neuron model as you like time step it across, um, your performance there is going to be governed by the number of kernel dispatches, which is related to like how much you unroll that loop. Um, so if you don't unroll the loop, if you just have like your one step recurrent function of like take in the previous time, decay the previous voltage value
Yeah.
and add the new spikes, um, like that it's a very cheap kernel to execute, and if you're running at like several hundred or 200 time steps for each batch, you're sending a ton of very lightweight kernels to the GPU, which then like forces you to become IO bound in a way because
Yeah.
you're like waiting on those kernels to process.
But that
Uh,
that makes sense because now also the compute graph is more complicated, right? So for instance, in the recurrent setting, right, you can't just execute it feed forward. You need to kind of execute it, cache the results, and use it for the next kernel, and so on and so forth. So what I'm hearing you say is we can take the entire time loop and then fuse that into a single kernel. That's where it makes sense. But couldn't
yeah,
you conceive? Couldn't the just-in-time compiler do that for you? Do you need Pallas for that?
that I don't think so, to be honest, because when you with JAX's scan operation, you can unroll the entire loop. So you'll pay a upfront larger cost up front in terms of unrolling all of the time steps of your neuron model.
Mm,
But once it goes to execute, you get better throughput because now it's keeping all the
it's
data
unrolled.
local, and
Yeah.
yeah, and like the JAX is going to fuse that like all of those steps together into like one loop or into one kernel to send.
Yeah.
Um, so like the speed up from the kernel there. Like I don't know if Pallas is going to improve your speed, for like this for inferencing normal neuron models. I think you'll see speed ups if you uh, deal with like the data loading process and how you're like loading in like unpacking bits and spikes into the model and then writing them out. I think there's probably some improvements there maybe.
Hmm.
I think there's room for improvement if you target like TPU architectures, because they TPUs, from what I've been reading, are more sequential in how they process arrays, which might be more conducive for like SNN style workloads, whereas GPUs are very parallel.
Yeah.
Um,
Of course.
but
Okay.
yeah, I mean,
But this
just
is
for like a
interesting.
little point of comparison, like if you don't just in time compile the function,
Good point.
so
Yeah. What then happens?
yeah, um, and at first I thought like I forgot to just in time compile the function. I'm thinking, holy cow, Pallas is like a free like speed up. But yeah, it's you get from just using just in time compilation, you can get pretty substantial speed ups of like 9x, like 5 to 10x basically, depending on the thing. Um,
That's pretty good. That's really good.
so like this, is showing that like the just in time compilation tracing is pretty good. But
Yeah,
yeah,
for sure.
the it seems like Palace like really comes in if you want to write like if you're using structured matrices or if you're using like if you want to target TPU and use like some sparse computation features, I think that's where you really need Palace, but you can get really good results from just using like JAX and trusting the XLA compiler for these dense operations.
But that's a
Um,
really good takeaway, right? Which means, I guess, like it's a great first step just to use JAX's JIT, and then when you then run into performance bottlenecks, you can explore something like Pallas to then really crunch on the hotspots. Right? But I
yeah,
guess,
because
sorry, go ahead.
I was gonna say because there's With TPUs, there's the ability to skip, or you can provide like a mask and actually allow the TPU to do data dependent computation, which isn't normally capable. You're not able to usually do that in JAX. JAX is very rigid about like the structure, like the shapes of your inputs have to stay constant in order to do all this compilation magic at a time. Um, but it seems like with TPUs, they have the ability to like prefetch scalar values and use that for control flow. So, for example, like what I'm thinking is, um, like we have our spiking Heidelberg digit data set, and
Mm.
like let's say it's 512 time steps long. Each of the like digits or like spoken words and all of those like samples occur like start or stop at different times and they have different lengths, and you end up with lots of like zeros in this like in your data set.
Yeah.
And you can save space by compressing those into like 8-bit integers to get like a pretty like almost 90% space savings. But still, when you go to unpack the batch and execute over it, you have situations where it's like, okay, well, the first like 200 time steps of this model are just computing zeros. Um, if you compute like a sparsity mask ahead of time that just shows the regions, like it's just a single bit or like a single value per like 16 time steps of the input sample of like where it's zero. I
Yeah.
think you can feed that into like the scalar processing unit on a TPU and then use that as a way to just
Oh,
like
that's
you can tell it to
interesting.
skip to the start of the dense compute region of like the voice sample.
So that, but that must be a machine instruction on the TPU to kind of being able to jump and hit like that, or
Yeah, well, so like what it would be is like you would use this like data mask essentially to signal like in the there's like a hardware unit for that loads ahead of time that you could load this mask into and then tell that use that as a way of instructing the TPU like yeah start fetching from this index specifically so you just start from the first like actually dense
yeah, the
like
actual. I mean, this is
yeah.
this is almost neumorphic, right? Because you have the sparsity, right? So you kind of avoid computation where you don't have it.
Yeah, and like I think like this hardware feature was built more around the idea of like you have um like say you have a 2048 by 2048 large matrix but you know that there's only some regions that are actually dense and others that are all zeros,
Mm,
like you could have like a sparse attention mask and then you only load in the specific regions that correspond to the attention mask and then
yeah,
nothing else, saving you like
a
a
lot.
decent amount of
Yeah.
matmul. You could use it in the same way for like having efficient load, just only computing over where the input actually is in this like like sparse spiking data. Um, so like that's like probably what the best use case of using Pallas would be for in the near future is just like using it for intelligent data loading and like on a TPU. Because also like yeah, I mean TPUs are just different beasts than GPUs. And I like not a lot of work has gone into like optimizing SNNs for TPUs at all. So
Yet, I feel like we should do a different hacking hour trying to get that working. That would be super cool. Although we would need a TPU, we have to go to Colab or something. But I'm
yeah,
wondering, like, do you want to try this also for leak integrated Fire Neuron? I guess it would also be fun to see how this could work for recurrent setting, right? Because then we would need the state somehow. Um,
yeah, that would be good. I have
or do
we don't.
do could this already feed into Spyx? I mean, the library. I mean, because I guess the speed up here using Pallas, even though it's a cool framework, doesn't really seem to be that attractive to integrate. At least for
Yeah, I mean
the
like I mean if we run these again and again, it's going to come out to essentially the same amount of time. So I don't know if there's really like fusing the surrogate gradient operations might not actually be a payoff at all. Or like you know like it's pretty noisy in terms of like whether it provides a benefit or not. Because I've also seen instances where the Pallas kernel is slower than the like just in time compiled
okay,
one. And this is like I picked Super Spike because it was the most. It seemed like the most complicated or had the most individual operations. Um, so in terms of like looking at spikes and like what could be like a target for I mean, for the reasons we've just discussed, it was like, well, yeah, like the if I'll copy paste in like the leaky integrate and fire definition from Spyx.
Yeah, so you just do the same, like copy it in, see what happens without any optimization, maybe with JIT, and then with Pallas.
Yeah, I think we'll just prune it down and we can have like a toy example outside of Spyx just for now because this like we'll have to pull in a lot of machinery to like actually
Mm.
execute like this
Yeah, so
as
you just
a
focus on the call function essentially.
yeah. But you can see here that really the between the fundamental operations are just you have like some pretty basic primitives here, and then it's the question of just like the recurrent state. Um, so like this, if we were to try to lower this, I mean, I guess that's what we should do here is lower this and see like what does the generated output look like. Um, I think, I mean, my notion is that there may not be an edge to like a Pallas kernel versus like the unrolled version of whatever just-in-time compilation yields us. But it's good to see if that's the case. Um,
But I guess that was the idea of the exploration, right? Kind of figuring out is there an advantage, and if there is, we can try to pull that into spikes,
yeah.
right? So I guess it makes sense to try. I think that would be fun. Um,
So we'll just make this a stateless neuron based on glyph. So we'll just provide in like X and V. Um,
and by stateless, you mean
uh,
you mean that you
like instead of making it a class,
yeah,
like a
no, so it's just a
haiku based.
function, right? So the state would be the
Yeah.
voltage in V essentially.
Yeah. Um,
So it'd be V minus some threshold, which could be one. Um, yeah, and then spike would then be, I guess, the heaviside function with the Surga gradient for backpropagation, right?
yeah. I gotta remember.
What are we importing?
I'm just pulling in the activation function or an activation function to use. Um,
Well, you'd want the heavy side, right? But I guess the question is whether it's enriched with um,
yeah. Well, I guess like which surrogate to use. I was just
yeah,
trying to remember
exactly.
the. Uh,
Great choice. I mean, maybe it makes sense here also to refer to your previous kernels, right? Because that might matter. No, I guess not, because you still be compiling everything to
yeah, I
HCL.
mean, like this super spike import here is just referencing. Um, it's a heaviside in the forward pass, and then the
The super spine in
literally
the
this
backwards,
granted
yeah.
super spike function from earlier.
But similar to
Um,
what we did before, if you then lower your current lift neuron into Pallas, for instance, right, then that would also inline, or um, it will also fuse that super spike code, right? So we don't,
yeah,
yeah.
I I'm not sure what'll. I'd have to check about what'll happen with the auto differentiation with Palace, but um, because there might be a nuance there that I'm not thinking of immediately. But
Yeah, I think that's pretty interesting though. I mean, there's also a lot of details here, right, to get right, because it's not just um, it's not just single instructions, right? It's about how everything ties together, and then also for a library, you want to make it modular, so you don't have to um, reinvent or recompile the wheel every time, basically. But
um,
but I'm very curious to see what happens now. Value era, that's great. Um, because this now is it's stateless in the sense that you just keep the state in the function call, right? But if you need a traced version of this, then I guess you would have some form of loop. Would you just for loop over it, or how do you deal with that?
um,
trace it
So
out.
now that with this stateless version, what we'll do is we pass it to JAX, like the scan operator in JAX,
Yes. Yeah.
um, and then that handles. So like if you were to just use a like say I wrote a wrapper function, had a for loop, and then called this like lift neuron function, and then I just in time compiled the like wrapper. Um, the Python native for loop would get statically unrolled the entire way, which depending on what you're shooting for is you may not want because that'll like you're going to generate a whole lot of code and you'll have a slow compile time.
Yeah, and I
Um,
guess that's the whole
but in
point
the
of scan
case,
operation you said before, right? You kind of scan it through in the beginning, and then that's an overhead first, but then it becomes much faster when you apply it.
um, well, that's referring to tracing is just the whole process of doing the just-in-time compilation. The scan operator in Python is what handles looping behavior. Um, because basically scan takes a function and an input, or you give scan a function, and then what scan does is it executes that function over like an input array and provides the output and like optionally the states, if I recall correctly. Um,
Okay,
and
yeah,
then
sorry, I think that suddenly was lost on me. So basically you're saying the scan is what provides you the unroll, no, sorry, the
yeah, scan is what handles like the unrolling of operations.
yeah, because it will give you a compute graph, which is then doing all the individual computations, like in a loop. But tracing then,
Yeah, tracing is like the compiling side of like determining all the operations in the computational graph and then like generating like the successive code.
okay, yeah, okay, because
Like
so it's not
tracing
tracing
is
in a
a blur.
mathematical sense, it's just tracing the graph in a traversing sense.
Yeah.
Yeah, okay, that's clear.
Like it traces the control flow, whereas the scan operator is what um, is a function that takes a function and then yeah. Um,
But then scan doesn't do any optimization. It just gives you a single function. Is that correct understood?
um, yeah, like the scan itself doesn't do optimization, but like what it does is it when it gets interpreted and compiled and all that jazz, what happens is like if you don't unroll the scan, like it'll make sure that it generates like it'll dispatch independent kernels for each of the like executions of the body function. Um,
Yeah, perfect. I'm realizing I'm grilling you hard here, but I really want to understand the subtleties. But this makes sense because now we want to scan this so we can get a single function which would kind of aggregate into a single object or a single call, and then that we can optimize.
yeah, I'm gonna jump quickly to a different notebook just to like help solidify the like meaning or the um so like in the training loops, for example, that I have in the documentation for Spyx, um, the scan function JAX lax scan takes a function, which is in this case the epoch function, and then it's like inputs are like the param or like the initial conditions are the optimizer state and the parameters of the SNN.
Hmm.
So those get carried. So it's like um, function, like the body function, the like
This
the
would be
carry
yeah.
function, and then like optionally like the input array. Um, and then so
And
what
it's
happens
optional
is like
because you could run it later, right? You could decide just to get the function out and then run it afterwards.
kind of yeah, like so like what happens is like if you don't like as this is like when all of this gets just in time compiled, um, what happens is epoch like a separate kernel gets sent to the GPU for every execution of epoch. If you were to unroll this scan, which you can do via like an argument, like what it would do is take all of the generated code within epoch, concatenate it into one massive kernel that would like tank your computer,
Yeah.
and then try to like force that to the GPU. Um,
Okay,
but
but
then
then
you can see like there are nested scans in here. So every time like these you see these scans which are not unrolled, what happens is the like body function is sent as like a separate like kernel to the GPU.
hmm.
Um, So usually like these train step, like the train step function, for example, you can see like it's unpacking the bits, it's computing gradients. Like it's a relatively, I mean, it's not meaty, but it's not a trivial amount, like unit of computation, so it's
Yeah.
efficient.
Yeah.
Um,
So
but like the SNN, like, or the neuron model dynamics, like those are extremely lightweight to the point that you are like slowing yourself down by sending them individually. Um,
yeah, for sure. I mean, this totally makes sense. I mean, but here's a naive question, right? Because I thought the idea of kernel fusion is that you're able to take consecutive calls essentially and fuse them into singular kernels. So why is it that you can't just see like what's preventing JAX or Pallas from realizing, okay, here's then a loop where I'm just doing the same thing over and over and over again. Let me just dump that onto us. Let me just fuse that into a single kernel and yeah, scan it out just like the
um,
scan. Uh, that's a very vicious question, I know, but in
yeah,
my understanding, this
yeah.
those, I mean, identically that diagram should commute, right? You should be able to first scan and then compile, versus then compile and then fuse. That should kind of give you the same result, no?
I think, yeah, I mean, I guess we can find out here if we just write
No,
this.
I mean, let's leave it here. Let's leave it here. I think it's totally fine just for now to say, okay, let's just scan this thing out because that gives us then this singular unit we can call. And if we're then trying to optimize that into a fused kernel, then I totally follow your reasoning that should be much faster to call. Um,
Yeah. Um, like it might be like if there's a way to write like the kernel, like a Pallas kernel, in such a way that it isn't like just massive copy pasting of the same code over and over. Um,
hmm.
and it that would be probably as fast as the massive like fused kernel, that's just unrolled. But
Mm.
hopefully it would be a lot faster in terms of code generation. Um, if that makes sense.
Yeah, I think I can see that. Yeah.
Um,
Okay. Yeah, but maybe it's also a subtlety we don't have to get into. I'm just very curious. I love this the idea of fusing code, right? Especially in the functional program, I think is one of the most beautiful things to do because so I've been writing a bit of Haskell, right? And I just love that way of thinking because that's exactly this, right? You can just from the functions know exactly what composes and what doesn't.
yeah.
But yeah, so now we're scanning it, and then you need the input, and I guess the input in this case would just be uh, the yeah. So you'd need some kind of timed array
And,
somewhere.
yeah, it'll be
These must be
yeah, it
the
should be.
voltages, right?
Yeah, it'll be like the first input and then a zero array. So it'll be
Um, okay, so it's this first voltage because it's this initial state. Yes, okay, and then it scans over the second parameter v so that it will update when you give it then as a third parameter the actual inputs for all subsequent time steps. Then scan will automatically kind of pass v forward. Is that correctly understood?
yeah,
Just
it's
like
I mean, let
fold
me
in Haskell, I guess.
JAX scan.
Am
Yeah,
I
it's just
stressing you too much, Kate?
no, no, no. We'll do it live. So the prototype for F is it's carry comma X in and then it's carry comma Y out. So the first
Mm.
unit to like scan like the glyph neuron here is like the carried value. Um, which I guess is like permuted from whatever IQ does for some reason. Um,
Oh, wait, what?
Yeah, so like the first
So the first
argument
is
to
the state value, not the input
yeah,
value. Okay. Okay.
yeah, so it's carry comma x. The output is um could be v comma spikes.
Yeah. Yeah.
Um,
And then we just need some huge array. Ah. Maybe how many time steps are in the spiking Heidelberg?
I mean, like a reasonable. I mean, we could do like 512 or like 128 or.
Yeah, that'd be fun. At least more than 10 just to see.
Why is this code cell not coding?
Yeah, that's a good question. I mean, in general, I feel like, I mean, it's wonderful you can do Jupyter notebooks here, but I feel like it's a bit jumpy. Also, like we saw before with the live sharing, it doesn't really work as well as with text.
Yeah, so then it's. I guess the state's only one thing. So just this should hopefully be fine, and then
Right, because
x's would.
so if you, for instance, like with 16 inputs, that kind of assumes 16 neurons, right? But will that broadcast? So if you start with a 0, will that then broadcast to?
This should be a one, like a single neuron.
Ah,
Um,
but why? Okay, I thought you wanted to have a separate. Okay, I thought first you give the. Now I understand. Yes, now I understand. Because then xn is not given in the first sense, because you don't need the. You're not providing the input, you're just providing the initial carry, like the initial state. And then the third argument would then be all the subsequent, like all the, the inputs. It's probably confusing to everyone else. I'm just saying things out loud to make sure I'm not misunderstanding anything.
um,
So what's happening now? I thought, I mean, if it's carry first, that would be the right way to
yeah,
instantiate
it
it,
was just
no?
like a syntax error with like the type of thing I was feeding in.
Does it have to be a specific data type?
Yeah, well, I was getting like a frame or something. Um,
A frame?
Usually it just means like something was materialized that shouldn't be materialized or vice versa. Um,
Unsupported
yeah,
operands.
so like it's trying to do like yeah, um, something in float. Like zero point 0.9 is the float, obviously, and then V, which is getting passed in, is like an XLA frame.
Could it be because the orders
Oh,
of the
here.
operations are?
Just scrap this for a second. What am
Could it be the order of operations?
Yeah, yeah, and let's
What's a frame?
I wonder if that they might have renamed like the tracer values or something in JAX or
Dynamic
not,
JAX
maybe.
per tracer.
Oh, wait. Oh, I'm silly goose me.
Ah, okay, because now yeah, okay. So we,
Yeah.
we can introduce the threshold again if you want, but it's fine. Let's just go.
Is it yeah,
That will
that was
make it okay. And you ran that cell, nice, yeah. Okay, ha. So our intuition was correct.
that's the end voltage.
That's really
And
cool.
then And then,
Beautiful.
yeah, I should change this to oh, Spyx.
Yeah. But that also means that this is then the kind of un or like it's like the just in time compiled version of the loop. Is that fair to say?
Yeah, so like this, the code for this should be like here, we'll like this should look like a some type of like the expression should have like a scan in it that'll then repeat the same kernel over and over, but it'll be succinct. It won't be unrolled. Um, so if we def like run with and then just fold all of this in, and then
Return it, right? Yeah.
actually, yeah, if we just return the
And then yeah, that would be the default. And then you could of course JIT.
oh, you can make X and an argument.
Yeah, and then you would yeah. So yeah. Can we maybe benchmark that versus? I guess you could also just in time compile this in principle, right?
Um, I forget the exact specifics, but I think scan implicitly JIT compiles the body function as part of its like functionality.
Okay.
When you scan like when you scan an operator, the operator inside gets JIT compiled.
Yeah, that would
Um,
make sense. So what?
so if you like JIT compile the outside, it's a little redundant, but you can do it with no harm. Um, but like if we do jax dot make under jaxper of run lift, and if I remember to actually like open this and then do x under n, yeah. So this is the geez. Okay, that's nice. Um,
Wow. Okay. Yeah.
yeah, so we can see run lift here with its carry value of 1, which this is the voltage, this is the input array that is traced. Then here's where you see the scan operation like open up. And then inside of here is going to be your neuron dynamics. Um,
Then you have a
so like yeah, so just to like help call out things more. Um,
yeah. I
so
don't know
you
if you
can
have to
see
go into details, but I guess like then you using your own surrogate function, which is why you have this VJP. Um, I guess vector
yeah,
Jacobian stuff.
yeah. So like this subtraction operation right here matches up with the threshold subtraction in the like right here.
Yeah.
Uh,
Yeah.
and then yeah, you see this like VJP open up. Um, and then so like the where operation here is doing the like efficient like have a side step function, and then the other half is going to be the like super spike backwards. And then you see down here like the x, y, and z, like these are the other lif operations, and then here's like the scan metadata. Um,
I mean,
so yeah,
this is
that's
very reasonable, right? It all makes sense. Does VJP actually stand for vector Jacobian, or
yep,
yeah?
that's exactly what that is.
Okay, but then in principle, right? We could benchmark that. Now we can see how long does that take to run those two things, right?
Yeah, let me just find the
You see, I'm totally itching for benchmarking, but it's I think it's a good heuristic, right? Because we're doing all these gymnastics and they all make perfect sense to me, right? But does it hold? Will it blend?
will it blend?
Will it blend?
Um, and it's just run. Oh, did I
Uh-oh.
forget something?
Tuple optic has no because the output is a tuple.
I got a block on one of the things.
Yeah.
Yeah. Uh, so that's 146 microseconds over like 16 inputs.
and that's if you make it into a JAX. No, that's not if you make it
Yeah.
into. Yeah, that's jigged, but it's not lowered.
No, like when you JIT and then call it the like that, it does go through the whole lowering process. It's not unrolled, but it is like lowered and just in time compiled.
But
Um,
so that's true. But doesn't that also count in the benchmark?
um, it should. I mean, it gets like the compilation process gets cached, so it should only impact like the first iteration
Yeah.
theoretically.
Yeah. No.
Um,
Okay. But okay. So I guess a meaningful comparison then would be towards Pallas.
yeah, I just want to take a peek at like the compiled lowering.
Yeah. Sure.
Uh,
And I guess that's reasonable because now we want to see if it actually fuses some of the operation.
yeah, so it's just dot lower the thing.
Oh,
So
that makes
here's
more
the
sense.
HLO.
Oh God.
Um,
Constant main. Okay.
yeah, so you can see like the logic in here is happening of like comparison. So
And
like the loop
it
is
seems to be doing a loop, right? There's a condition and do statement.
yeah, and then this should be the active like the surrogate gradient function here, I believe, because it's the where, and then
Ah, yeah, it would be the threshold. Yeah.
yeah,
Okay.
yeah. So it looks like the body function gets seems like it's nested or like within this the scan loop that's in the main of the, and then I imagine if we do the compiling, so see what kind of gets fused in here.
Yeah.
Um,
That seems it's a bit easier to read, isn't it?
yeah. So like these should be like all of the distinct kernels that get sent to the GPU, and then they call each other as the program, essentially. Like there's probably like another layer or so of like translation going on before it hits metal, but like this is the XLA output. Um,
I mean, just a really dumb question, right? Do you actually specify that you're running it in GPU? Couldn't this be done also for CPU in principle?
yeah, this could be CPU or
But did
like
you
it.
in your
I know
vectors? I didn't
it's by
notice.
default going to be on the GPU though.
Okay,
Like the
good,
default is the GPU.
good, good, good.
Like you'll know if it's not running on GPU because you'll see lots of nasty grams when you try to run your first like operation of the notebook saying like, "Hey, we're using the CPU because something's wrong."
Okay,
Um,
that's really useful. Yeah. Um, okay, so but is this pretty much what you expected?
yeah, I mean, I'd probably have to just read this like compiled stuff a little closer, but yeah, I mean, so if actually just for compare, I mean, I know it's gonna pain you to generate more code and not execute it. Um, but if we were to do an unroll, um, so if we make a second version of this,
Mm.
uh, so now this will completely unroll this loop for like the max number of iterations. And
Okay.
now if we take this and do the same thing, but we use runlif unrolled,
Unrolled. Yeah.
it should be big chungus. Yeah.
That's pretty much what happened. You still have like one call, but yeah. Wow. Okay.
So that's really the difference in like, so scan basically translates into XLA level loops, and then if you unroll it, you get really massive like code generation.
Yeah.
So like it's faster to completely unroll very lightweight kernels like the neuron dynamics, um, because essentially at the level of the neuron dynamics in a layer, like all you're doing are like simple arithmetic operations, including like the surrogate gradient
Yeah.
backwards pass.
Yeah.
But then once you get to like the gradient computations and like the actual like batch level, then like you really start to blow up the compilation. Um, but yeah, so like if we here we'll benchmark the unrolled.
It's really neat to get this level of insight, right? Because you can really start to play with each component and see what matters. Because Jesus Christ, that's like that's like a
Yeah,
factor 5, right?
yeah, and that's the speed up just off of cutting down the
The
number
loops.
of dispatches.
Yeah, which yeah, okay, yeah, that's a good point. Because I mean, even though there are different dispatches, like I think okay, maybe what I'm just struggling to understand exactly what the cleverness can and cannot do. Because in principle, you could just say, okay, all these kernels may be separate, but we can kind of fuse them into one, and we can kind of just send all of them at once and run them. But it somehow doesn't do that.
Yeah.
I
Yeah,
mean,
I'm
yeah,
not
again,
entirely
that
sure.
maybe that's something we have to explain. I'm just trying to get an intuition for where you have to optimize, basically. So what you're saying, if by printing out the code, you can also see the number of dispatches, which means many dispatches is just intuitively bad.
Yeah, so like the the verbosity, like the amount for which the more code you see like in this unrolled version, um,
The better.
like the more you see unrolled code, yeah, I mean the better in terms of like you're sending, like you just send this entire thing once to the
Yeah,
GPU,
yeah.
rather than like, well, because each time my understanding is JAX synchronously dispatches each of these kernels to the GPU like in order.
And that's
Um,
probably the problem, right? Because for this to be efficient, you have to do that once.
yeah,
Yeah.
yeah. So like I think when you have, yeah, it's just a question. I like, it's a nuance in like the GPU controller versus the CPU and what's getting sync. Like, yeah, it's I don't have the visibility all the way in to know exactly what the how the kernels are getting executed within the GPU. Because like yeah, it does seem kind of weird. Like, why is it expensive to like send, like, are kernels getting sent from the CPU every single time for every single body of the loop? Like, why is it that way and not like you have the body you just cached on the GPU and it's just re-executing?
Right.
Uh,
But I mean, it's also like maybe you don't have to go too much into it, right? I think it's just really good to know here are the tools you can export, and the benchmark speaks a clear language, right? Like this is clearly much better. I
yeah,
wonder if we have time to quickly try a Pallas version, right? Because what happens then if we can kind of write all of this stuff in Pallas somehow? Do you think
yeah.
that could
So if
benefit it?
we, I mean, it might. I mean, it shouldn't be too hard to quickly try.
Because we
Um,
already have the super spike. I guess we can rely on that. We just need some kind of thresholding mechanism. Um,
yeah, if I excuse me.
Bless you.
Uh,
Because that, I mean, if according to my understanding, right, that should also be able to do all this fusion business. So in principle, if you can do that, then Pallas would know exactly what to, um, yeah, what to optimize. And my understanding is also that that would be similar to one of the use cases we talked about before, where it would make sense to use Pallas, namely in this kind of recurrent, kind of more complicated graph structure compared to like just the boring sequential execution we had before.
Um, this is functional, so it should. Actually, no, I can't just reuse this as the kernel outright. I can reuse pretty much all of it, but I have to modify the syntax. Um,
Um,
because we have to use references instead of.
yeah, okay, but so you can't just use existing JAX functions in Pallas. Like you have to write once you go Pallas, everything has to be Pallas.
Um, well, actually, I mean, this is. I mean, it might be worth a shot. Since you can use JAX operations inside of Pallas, you might be able to literally just write Pallas wrappers that handle like the references like in and out, and then you just call the JAX function within the. Like I think I should just be able to call like the lift neuron function inside of this, and then just write the outputs back. You know what I mean?
Yeah, yeah, but yeah, yeah. We could
Um,
try that, but yeah, as you prefer. I wonder whether that's. I mean, you wouldn't. Would you do that normally? Like, is
I
Pallas able
mean,
to optimize that? Basically, is my question.
it
Because
should. I think.
I mean, let's
Um,
try.
yeah.
That would be cool,
Let's.
right? Because then you can reuse your code. But if Pallas uses the assumption that you write things in Pallas style, and you can't just use the other kernel, then that's going to be very expensive because in principle you might risk leaving the kernel to do a different call somewhere else.
Yeah, I think the problem. Also, Palace, the like big focus is on like you're now dealing with like blocks and like the actual shape of the hardware. But since a lot of this stuff is well, actually in the case of like a neuron model, I mean, I think you could just pass it in and out. That may not be the best. I don't know.
There's so many questions, Kate. It's crazy. Let's just do whatever is easiest. Whatever you want to do. Um,
Yeah, it's lift neuron VX. We'll just make these capital to be consistent. So actually,
awesome.
and then it should hopefully just be
I love your editor tells you that something is wrong. It's really handy.
uh, come on, brain.
You can just do VX, right? Yeah, we've also been at it for a while. Like it starts being really um, at least I start being a little sluggish. Um, okay, but this makes sense, right? Because you've gotten the new values and you've reassigned them into your output references.
Yep. And then so that's the and then we just need Palace and lift. and then it's gonna be left kernel, and then really it's just a game of making sure we get the input shapes right. Um,
Jens,
yeah,
to your question regarding Pallas
Hmm.
and whether you could like use JAX inside it. Since Pallas is lower level and it restricts the backends that you can use, it only works on GPUs and GPUs.
Mm.
Um, the idea is that you could mix some Pallas with JAX, but if you're writing Pallas, you're readily restricting your targets. So yeah, it's kind of if you're writing some Pallas kernels, you can still use them alongside JAX stuff, but you are de facto signing up for the backends that work with it.
So if I'm understanding correctly, that means that you can actually do it, but if you try to then jump to different devices, then you run into trouble.
Yeah, Pallas is really lower level than JAX. Kind of like writing directly in some sort of language that is inside the machinery of
Yeah,
JAX.
yeah.
So yeah, you wouldn't like the whole point of writing something in Pallas is that you can go beyond what the usual JAX API lets you do.
yeah, yeah. Like the super spike function, for example, uses like JAX numpy absolute value as part of the operation. Um, but yeah, that makes sense in terms of like if you end up using JAX inside of Pallas, then you're kind of like circularizing back into ecosystem. No idea if
Yeah,
this is going to
I
work.
mean, I feel like I can interpret that in two ways. Like, I can either interpret to mean like if you write JAX and everything is in that ecosystem, you're good. I can also interpret it to mean like, okay, Pallas is lower level, so if you write something that's higher level, it's gonna complain because it doesn't realize whether it's exactly it's providing the same guarantees essentially.
Um, and I don't have any personal experience with it. I'm just reading through the documentation.
Yeah, it's super helpful. It's super helpful.
But yeah, what I understand is that they compose fairly well together. So
Okay,
you can
that's
have
amazing.
90% of JAX. Kind of, I see it like a low-level extension for Python. It doesn't mean that your whole Python is going to have to be written in C++, but you can have some of it written in that language. By the same token, if the entirety of your Pallas function can be expressed in regular JAX, then you might as well write a regular JAX function, I think.
Hmm.
Unless there's another, or to my understanding is that Pallas gives you access to lower level constructs that you can leverage to get better performance. But the whole point is to use those. If you're not using them at all, if basically your function is a one-to-one mapping to some sort of JAX function, then you might as well write in JAX. It's going to be easier and probably boil down to the same thing.
Yeah, that's a really good point. But I guess that also implies then that the only reason to use Pallas would be when you have a need for those low level functions. So if you can express
Mhm.
everything in JAX, then um, like you don't need anything else.
Oh yeah, absolutely. Yeah, so the whole idea is that if you're writing some Pallas, it's probably because there's a limit in JAX that you want to work around through that lower level framework.
That's a little
Well,
interesting, yeah. Because I mean,
Yeah, I think
it almost means that I mean, since JAX is more or less implementing the NumPy API, it more or less means that if you can't do things with NumPy, then you need Pallas. Ish, right?
yeah, I think it's like especially if you want to target TPUs and try. I mean, if you want to write the equivalent of flash attention for TPUs, you need Pallas. Like if you want to do things like pipelining or more,
Mm.
like especially the like scalar prefetching thing I was talking about with like sparse structured matrices. Um,
Yeah, okay, yeah, and that's exactly to your point as well, Alexander, right? Because then you're doing something which is JAX doesn't have an understanding of. Then you need to know that you're on TPU, and that's only for TPUs.
yeah, I just think that the like dense matmul style things that are usually well covered by GPUs are probably already well covered by um, like JAX and XLA should already handle like basic like most matmul style things pretty damn well.
I feel like you're not
Um,
selling Pallas very well, Kate.
well, I mean, I'm learning it as I go. Like I mean, I think that there's probably like a really fruitful direction in terms of using Pallas for TPUs. But yeah, I mean, I guess that's the disclaimer. Like, I'm a huge proponent of JAX. I don't have a. I'm figuring out Palace's.
No, 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 and
I,
and
I
you
don't.
don't have
I
to,
don't know
right?
if Palace is the answer. Like, I'll say
I mean, I
I
think
don't think.
what I love about this is that we're talking things through as we go, and I'm definitely learning a lot, right? Because there's a lot of nuance here, which I have. I mean, as you can tell, I haven't been working with JAX for too much. But what I think is fascinating also is that there are many different options, right? Just by you can just try it out, right? It's not overly complicated, and then you just need to benchmark it to figure out what kind of works. What's happening in the code? What's the problem at the moment? In Spyx must be pipe. Oh god.
Uh,
So it seems like it's looking for a tuple, but it's getting a
uh,
singular.
yeah, it's
Is that because
so like you have to specify
out X?
like the blocks shape specification for the inputs and the outputs, and like
Ah. And I guess now
this is
you
like a
you
two
you you
thing.
actually you have two in, but don't you also have two out? No. Oh yes, you do in the lift kernel, right? There's out V and out X. Well, in the
Like
specs.
those are arguments, and then oh yeah, but this here we only want the output. We'll just take the output
Yeah,
spikes.
yeah, that should be fine.
Um,
Missing out X. Out X, that's the final. Ah,
because
yes.
I
Of course.
dropped the one thing.
It never ends. Oh, it's a different
Again.
one. That's good. Oh no,
Just
it's not an error trace for once. Excellent. Fantastic.
or maybe it is because it just vomited a.
Oh, really? Ah.
Oh, looks like that's the JAX per.
Okay, so this answers the question whether we can chain these things, which seems to not be the case.
Yeah, this is the issue. Is the VJP of the surrogate gradient that's bound together. That's the like punch I had earlier was like I wasn't sure about how the because we have the surrogate gradient like the super spike function is bound together as like the heaviside forward and super spike backwards, and this error is because the like Pallas doesn't understand the custom VJP binding of
Mm,
heaviside and super spike. Um,
yeah.
so
Okay.
this would require, yeah, I mean,
No, but this
this
makes
might,
sense, right? Now we've learned that. That makes sense. But that also means that if you want to do the super spike, you have to make the super spike kernel Pallas, right?
um,
Or avoid using the VJP.
grad of Pallas call. It might be a situation where you have to, um, like Pallas call of custom VJP might not work. But if you basically write like the forward kernel and then a separate backward kernel and bind them together with VJP, then you'll have like what you need.
Mm.
Um,
Yeah, but that seems like a bit more involved. I mean, we've been going at it for 1 hour and 40 minutes almost, so
yeah.
it may make sense to call it quits. But I think, I mean, I at least learned a lot, right? And especially this kind of comparing all the different um, the different optimization strategies, like whether to JIT and lower and trace and scan, I think has been really helpful for my understanding at least. If you find time to do the Pallas version of spiking super spike, I'd love to see what that means. I mean, now with the scan we got down to, was it 30 microseconds? It'd be really fun
Yeah.
to see what happens if you did this with Pallas. Um,
Yeah, I mean, my 2 second take would be that, like, yeah, you can try to keep optimizing at the, like, other than if you try to build hardware aware algorithms for TPUs where you could maybe do some smarter computation about skipping regions of zeros, you may not be able to get, you're really at the bottom of the barrel of Amdahl's law in terms of like micro optimizing
yeah.
like the neuron dynamics. And you'd probably get fast, like much more substantial improvements if you just worked on like parallel spiking algorithms that, are non-recursive or non-recurrent, um, such that you could like compute the spiking dynamics all in parallel or approximate them, do some type of like pre-training to get like the SNN into a roughly right area and then fine tune with actually recurrent computation.
Yeah.
Like I think that would be a much faster way to go about things,
Makes sense.
than to like, just like approximate in parallel in the beginning and then fine tune in recurrent versus like training the entire thing in recurrent. But um, I think that would give you much better like runtime savings than micro optimizing the like recurrent kernel
Yeah.
for GPU, because the GPU is still not going to be like the architectural paradigm just isn't in your favor in that case.
No.
Um,
No, that's true.
The Pallas documentation points out that it can be quite good at optimizing the loading and writing of very large arrays when really reading from memory becomes the bottleneck, which is potentially the case if you have a big SNN and you have some knowledge of the connection matrix. So if you know that some trunks in your SNN can run independently for a little while, for instance, or they're fairly isolated, you might be able to optimize that with Pallas, but not JAX, by using that information to load those chunks of memory together, that sort of stuff. That's fairly low level and probably very specific to some networks.
yeah. And in the same vein, like the scalar prefetching and skipping zeros with TPU might be like that's something that you need Pallas for. Um, and then like there might also be benefits, like I mean we could try to disambiguate what it looks like when you just like JIT compile, because like with Spyx, for example, the one thing you can do is like pack all of your data into integers and then unpack it per batch at like train time or inference time. Um, like I wonder if there's any benefit to be had out of like fusing together the bit packing or bit unpacking operations plus the like feeding it into the first linear layer, like same way you can fuse activations and map moles, like fuse
I
the
see.
data unpacking and like map mole for like the first linear layer. um
Right.
Unclear how much of a benefit that would be, but that would be something that would require, like if for some reason the JAX NumPy unpack bits operation doesn't fuse well with like the dense map mole,
Mhm.
like having some kind of combined layer there would save like a memory read write, which could be useful.
Super
I
fascinating. I mean, let's close down. But I have a final question of you, Kate. Knowing all this, do you think you'll consider using Pallas in Spikes?
Um, yeah, like I think if I run down the or like keep running down the idea of like TPU aware
Yeah.
SNN inference, like that would be like the perfect use case. But um, like that's something you can only really use. Like if you want to maximize the usage of TPUs, you would need something in JAX and you would need Pallas, and like that would be a good use case for Spyx to make it more unique. Um, so like that's something I'll continue to look at, but I don't think I'll like try to refactor all the rest of the library to accommodate Pallas level kernels for something that JAX seems to be doing pretty well.
It does seem to be doing pretty well, right? It's actually I must say I'm surprised, right? Just the normal jitting seems to be extremely efficient. So, but I think Kay, we should slowly close it here. But thank you so much for joining, and Alexander, thank you for
thank you for having me.
sticking along and asking great questions. So I'll see you around.